Hello, I'm Reed Miller, and this is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to observe and better understand magnetic fields through visual representation, to visually observe the relationship between distance and magnetic field, and to use the distance of magnetic fields and the Biot-Savart law to find the magnetic moment of a bar magnet. The fundamental physics we're going to use, we're going to represent a bar magnet as a magnetic dipole moment. We're going to use the Biot-Savart law and this is dependence on bar magnet equation shown there. The result of the lab is that the magnetic moment of the bar magnet is 2.08 amperes times meter squared, and that n equals negative 3.043. The model for this lab is that the bar magnet acts as a magnetic dipole in order to apply the Biot-Savart law to it. The system is the bar magnet, the surroundings are everything else. The initial conditions we have are the bar magnet and the magnetometer on our phone. So to begin, we need to find the precise location of the magnetometer on the phone. We do this by standing at the bar magnet and meter stick as shown in the figures, and moving the phone perpendicular to the bar magnet and finding where that gives the highest magnetic field reading. And where that is, we put a piece of tape across the axis where it happens, and then we turn the phone 90 degrees and do the same process. So now we have two pieces of tape, and where those pieces of tape cross is the approximate location of where the magnetometer is on the phone, and we can use that location to get a better reading for further measurements. For the main part of the experiment, we set up the bar magnet and phone on axis with each other. And then as we brought the phone closer to the bar magnet, the magnetic field readings from the magnetometer increased, and then vice versa. So we were able to track and correlate the distance between the bar magnet and the phone and the magnetic field rating on the phone. And we were able to track that in the table below. And when you graph a linear line of that by graphing the natural log of the magnetic field versus a proportional slope constant times the natural log of the distance, you get a linear line, and you can use the y-intercept and slope of that linear line to do further calculations in the further slides. Then we found the off-axis magnetic field by finding the on-axis distance that gave us a reading of 100 microteslas. Then we shifted the phone vertically that same distance. And then we tracked the y and x components of the magnetic field in the table below. And then we had to subtract the y component of the magnetic field due to the Earth, since we were not oriented a certain way to cancel that out. So we just subtracted that, and we were able to find the net magnetic field off axis at that 45-degree angle from the bar magnet. Calculations we get from the earlier slope on the graph, we get y equals negative 3.051x minus 14.691. The slope of that line gives us the n value, so that's negative 3.043. The y-intercept is equal to the natural log of k, so we get k equals 4.167 times 10 to the negative 7th. To find mu, we're going to set the middle equation on the right equal to the bottom one. Since we know k, we know n, and then we can set r equals 1. And so when we do all that, we solve for mu, and we get mu equals 2.08 amperes times meter squared. Here's my GlowScript code. The bottom function is the dipole B function, which finds the dipole moment at each location. Here's the different arrow objects at different locations. Here's the one at 45-degree angle to the bar magnet. And here's the visual, with the center being the magnet. Different arrows representing different locations in the magnetic field at that location. The values on the right are the calculated ones, and we calculate earlier in the experiment at a 45-degree angle to the bar magnet, and then you can compare those to the bottom ones below the visual. There's a pretty big discrepancy between those values. The sources of error is that the magnetic field of a bar magnet may have a very tiny discrepancy being represented as a magnetic dipole moment, but it's a very close model. Also, the magnetometer location on the iPhone may not have been precisely found. Even just being off by a few millimeters or so will affect the distances and magnetic readings we found. Also, not being exactly calibrated to the Earth's magnetic field will cause that magnetic field contribution from the Earth to skew some of the readings we found. So what if we hadn't oriented our experiment to compensate for magnetic north? Well, the Earth's contribution for the magnetic field would have skewed the values we got by just adding on an additional magnetic field contribution from the Earth. So one way we could have compensated for this would just be by subtracting the x component of the magnetic field from the Earth we found, kind of like what we did finding the off-axis magnetic field. And what if we were to stick two identical magnets together end to end and run the experiment again, If we did that, it's estimated that the magnetic field around those two magnets would be roughly doubled. So we can say that our measurements, we would expect them to be roughly doubled as well. And that's all I have. So thank you.